Today's lesson, Lesson 13, Part 2, the definition of scientific notation. Our learning targets for today, I can tell whether or not a number is written in scientific notation. And our second learning target, I can write large and small numbers in scientific notation. So what are standard notation and scientific notation? So a standard notation is the normal way to write numbers. It shows the place value of each digit. So if we were looking at this number, this would be 450 billion. How do we know that? We can count each place value. So we have ones, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions, 10 billions, 100 billion. So we'd say our number 450, 100 billion. Or we have this tiny number. When I say tiny number, I mean that the number in front of our decimal is a 0. So how we would say this is 76 billions. And how do we know? We have to count the place values. So it's tenths, hundredths, thousands, 10,000s, 100,000s, millions, 10 millions, 100 billion, millions, billions. So our last digit, the 6, is in the billions place. So we say our number, these are all zeros, so we just say 76 billions because our last digit showing is in the billions place. Both of these are called standard notation. That's the typical normal way that we see numbers. Now, scientific notation is just a way of writing these numbers using powers of 10. It's a lot more convenient way of writing numbers that are really big or tiny. So here would be an example, 4.5 times 10 to the 11th, or 7.6 times 10 to the negative 8th. Both of these correlate from what is above in standard notation. So instead of writing 450 billion, we could just write 4.5 to 10 to the 11th. We don't have to write all these zeros, which can be really confusing. The other way, instead of writing it out as 76 billionths, we could write it in scientific notation, 7.6 times 10 to the negative 8th. Notice the difference of our exponents. One's positive, one's negative, both to the power of 10. But the positive, when we're looking at numbers that are large or larger than 1, we use positive exponents. Negative exponents are smaller than 1. So this is a really, really tiny number. So we use negative numbers, and we'll learn more about that soon. So scientific notation and standard notation are just two different ways to write the same exact number. So if we had 4.5 times 10 to the third and 4,500, there are two different ways to write the same exact number. We had 3.89 times 10 to the negative 6, and 389, this would be tenths, hundredths, thousands, 10,000s, 100,000s, millions, 100 millions, or 10 millions, and 100 millions. So we say 389 hundred millionths is the same as the 3.89 times 10 to the negative 6. So once again, there are two different ways to write the same exact number. So there are some rules that we have to follow when writing numbers in scientific notation. So here are some rules. Numbers in scientific notation will always be written in this format. A times 10 to the nth power. So where A is, this number has to be greater than or equal to 1. So the number in front has to be at least 1, but less than 10. So it has to be a single digit number in front. So another way to think about this is there can only be one number in front of the decimal, but it can't be 0. For our exponent, it must be a positive or negative whole number. This has to be a whole number. So let's practice identifying scientific notation. So is this in scientific notation? 3.45 times 10 to the 8th. Yes, it does. We have, how do we know? This number in front, the 3, is larger than 0. So it's less than 10. And this 8 is our exponent, is a whole number. 10.6 times 10 to the 4th. Is this in scientific notation? No, it is not. The reason? This number is supposed to be less than 10. So to correct that, we'd have to move our decimal one more place over. So one more over, so it would become 1.06 times 10 to the negative 3rd. Now this is correct. It's one digit in front. That's bigger than 0, but less than 10. 1.99 times 10 to the 2nd. Is this in scientific notation? Hope you're picking up. Yes. It's only one digit in front, and it's bigger than 0, and it's a whole number for exponent. 0.3 times 10 to the 4th. Is this in scientific notation? I hope you said no. Why? Because this number is supposed to be greater or equal to 1. This front number. So if we corrected that, we'd have to move our decimal one more place to the right, which had become 3. 3 times 10 to the 3rd would be our correct example of making this in correct form of scientific notation. And notice when we move our decimal to correct these, our exponents has changed. It changed by a 1 place value, a 1 factor in this example. Is this in scientific notation? 15 times 10 to the 9th. It is not. This number is supposed to be less than 10. So if we correct that, our decimal, right now our decimal, when you don't see it, it's always at the end here. So it's 15. So it has to be, we have to move it one more place in. And when we move that decimal in, it changed our exponent from a 9, it now becomes a 10. Is this in scientific notation? 1 times 10 to the negative 9th. It sure is. 1.002 times 10 to the 12th. Our number's getting our decimal back here is getting a little longer than what we're used to. It sure is. It is correct. 3.8 times 10 to the 0.5 power. It is not in scientific notation. This exponent must be a whole number. This is the decimal. Nope, that will not work. So let's practice converting from standard notation to scientific notation. So let's start with converting large numbers to scientific notation. So if we have, how we'd say this would be 937 million. We don't want to write that full number out. We want to put it in scientific notation. So first what we need to do is move the decimal so that it has only one non-zero number in front of it and leave off the zeros. So if we did that, we're going to start where our decimal is. Our decimal's here. We're going to move our decimal all the way until we only have one digit in front. That's not a 0. So our decimal is going to go right here at 9.37. And then we're going to drop off all the zeros behind it. 9.37. So now let's count how many places you moved the decimal. So we moved it 3, 6, 7, 8. We moved it a total of 8 places. So the decimal is located at the very end where you can't see it in this one. So this number will be the exponent on the power of 10. So let's put it all together. It would be 9.37 times 10 to the 8th power. This exponent stays positive because it's a large number. Neptune is approximately 4.4 billion kilometers away from Earth. So in standard notation, it would look like this. 4.4 billion looks like this. 4 billion, 400 million. That's how we would say this number. So 4.4 billion. Let's put this in scientific notation. So let's start by moving our decimal so that only one number is is in the front. So we're going to move our decimal out here, keep going. It's going to land right here, where there's only one digit that's not a 0 that will be in front of our decimal. Right there. So now what we have to do, and we're going to say 4.4, and we're going to drop all the zeros behind it. Now we got to figure out how many place values, or how many places we move the decimal. This will become the exponent on our power of 10. So we moved it 3, 6, 9. 9 places. So that would be our exponent. So it's going to be times 10 to the 9th power, since we moved it 9 places. So there's been approximately 4 million negative coronavirus tests worldwide. That means 4 million people tested do not have the virus. So 4 million looks like this in standard notation. Let's put that in scientific notation. So let's start by moving our decimal until we only have one digit in the front. So our decimal is going to fall right here between the 4 and the 0. Now let's count how many place values we moved. Our decimal's here, so we moved it 6 places. 1, 2, 3, 4, 5, 6. That's going to be our exponent for our power of 10. Since we moved 6 places, we're going to say 4.0 times 10 to the 6. Another way we can write this, since it's 0, we can just say 4 times 10 to the 6. Same answer. Being that this is a 0, we can drop it off and just say 4 times 10 to the 6. Either way would be correct. So let's try these. Please pause the video and put these 4 examples in scientific notation. All right, let's go over our answers. So if we remember what we need to do, when you don't see a decimal, it's always at the end. So we need to move our decimal until we have only one digit in front. So our decimal is going to fall right between the 1 and the 2. It's going to be right here. And we're going to write out all the numbers that are non-zeros. So it would be 1.287. And when we have our decimal here, we're going to count how many decimal places we actually move. We move 3, 6, 7, 8, 9. Total of 9 places. So we're going to write it as 1.287 times 10 to the 9th. Notice we dropped all these zeros, but I kept this 287. It's important to keep all non-zero numbers in our place value, or in our scientific notation. Let's look at the next one, 9,300,000. So we're going to move our decimal from the very end to in between the 9 and the 3. We always want only one digit in front. That's not a 0. It has to be has to be 1 or less than 10. So 9.3, and we moved it a total of 1, 2, 3, 4, 5, 6. 6 places. So it's 9.3 times 10 to the 6th power. 8,000. Our decimal's here. So it's just, you can write it as 8 times 10 to the 1, 2, 3 times 10 to the 3rd. Or you could write it as 8.0 times 10 to the 3rd. Either one of these would be correct. This one, we have 29 billion, 10 million. How would we write that? So we have a little bit of mixed numbers here. When I say mixed numbers, that means we have a 0 in between some non-zero numbers. We have a 0 between this 9 and the 1. We have to include the 0 in this one. So our decimal is going to fall between the 2 and the 9, so it's 2.901. So I'm going to count how many place values. We went 3, 6, 9, and one more is 10. 10. So don't leave out zeros that come between non-zero numbers. So we didn't leave out this 0 because there's a 1 after it. But notice anything after that were all zeros, so I drop those off. I don't include those. If you're getting hung up on these, please contact your teacher for more help. Moving on to converting small numbers to scientific notation. So how do we say this number? So we have the tenths, hundredths, thousandths, 10,000s, 100,000s, millionths, 10 millions, 100 millions, billionths. So we would say this as 532 billionths. There's a TH at the end of the number. So what we need to do, we want to convert this into scientific notation. So I want to move my decimal all the way until I have a number so that move the decimal so that it has only one non-zero number in front of it and leave off all the zeros. So our decimal is going to fall between the 5 and the 3. So it'll be 5.32. Now notice this is a tiny number. And how do we know it's a tiny number? It's because there's zeros in front here. All right, our next thing is we have to count our decimals. So we moved it 1, 2, 3, 4, 5, 6, 7. Remember our decimal is going to fall between the 5 and the 3. So we move a total of 7 places. This will be the exponent of the power of 10. So how will we put this all together? 5.32 times 10 to the negative 7th. So we put this negative sign in here because the number is tiny or small. So our front number in scientific notation is going to act the same way as what we practice for large numbers. It has to, our number in front has to be the number 1 or a number less than 10. And our exponent has to be a negative number when we're dealing with small numbers. Very, very small numbers. So here's some examples. The 2004 Indonesian earthquake slowed the rotation of the Earth, making the length of the day 268 hundred millionths of a second shorter. So what would that look like? 268 hundred millionths of a second shorter. So this is how this is what it would look like in standard notation. Well, let's translate that into scientific notation. So the first thing, let's move our decimal so that there's only one number in front of it. So I'll move my decimal all the way until it's going to go right between the 2 and the 6. Because I only want one number in front. That's a 1 or a number less than 10. So we always only want one digit in front of the decimal. So it's going to be 2.68. Now let's count our decimals. We moved it 1, 2, 3, 4, 5, 6 places. So 2.68. Since we moved it 6 places, and it's a tiny number, we're going to say times 10 to the negative 6. A strand of human hair is 99 millionths of a meter thick. What would that look like in standard notation? Right here. 99 millionths. This last 9 would be in the millions place. So let's translate this into scientific notation. So I'm going to move this decimal all the way until we only have one number in front of it. It's going to go right here. 9.9. How many decimal places did we move? 1, 2, 3, 4, 5. 5 decimal places. And that's going to be our exponent. And notice it's going to be negative because this number is tiny. It's 0. That's how we know it's tiny. So we're going to write this as 9.9 times 10 to the negative 5th. All right, so I will want you to pause the video and try solving each one of these 4. Write these numbers in scientific notation. All right, let's go through our first one. So this is, let's figure out what this number would actually read. We have tenths, hundredths, thousandths, 10,000s, 100,000s, millionths, 10 millions, 100 million. So we'd say 379 hundred millionths. I want to put this in scientific notation, so I'm going to move my decimal until I have a number that's a non-zero. So this number has to be, and it has to be a 1-digit number that's going to be in front. So our number is going to be between the 3 and the 7. So we're going to write 3.79. And we're going to count how many decimal places we have. 1, 2, 3, 4, 5, 6 places. And since it's a tiny number, it's going to be negative 6. So it's 3.79 times 10 to the negative 6. Let's look at this one. We had to move our decimal all the way in between the two 4s. This first 4 is going to be our whole number in front. And how many places do we go? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it'll be 4.45 times 10 to the negative 11th. And make sure it's negative because this number is a tiny number, meaning that it's 0 in front. All of these are going to have a negative exponent. So this one we're going to move to after the 7. And we moved it 1, 2, 3, 4, 5 places. So 7, you could say 7.0, or you can just say 7. So 7 times negative 5 because we moved it 5 places. Or you could say 7.0 times 10 to the negative 5th. 7 times 10 to the negative 5th, or 7.0 times 10 to the negative 5th. And our last one, we're going to move our decimal to right in between the 8 and the 0. Notice we have to hang on to this. We're going to write 8.08. We have to include zeros that are in between non-zeros, so between these two 8s. So it's going to be 8.08. Let's count how many zeros we have. We moved it 1, 2, 3, 4, 5, 6, 7 places. So 8.08 times 10 to the negative 7th. So just make sure you don't leave out zeros that come between non-zero numbers. If you're getting hung up on these, please let your teacher know. So in general, a large number gets a positive exponent. So if we had the number 4,500, it becomes 4.5 times 10 to the third. Positive exponent. It's a big number. Small number gets a negative exponent. We had to write this. So this would be tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millions, 10 million. So 389 10 millionths, we would say. We want to put that into scientific notation. Move our decimal, put it between the 3 and the 8, so 3.89. We moved to a total of 1, 2, 3, 4, 5 places. And it's going to be a negative exponent. So it would be 3.89 times 10 to the negative 5th. And being that this number is small, how do we know it's small? Because there's a 0 in front. It's still a positive number overall, but our exponent's going to be negative because it's our whole number in front of the decimal is a 0. All right, so that's it for today. We want you to head on over to the Schoology to practice. Email your teacher if you need any extra help. Have a good day.